At this point, we now know that there's a new model of the atom based on Thomson's findings that there are particles inside the atom that are smaller than the atom that are negatively charged and that can move, and that those negatively charged particles are balanced by a positively charged substance that makes up the rest of the atom. And that's kind of the model that we're working with here. We have also seen that certain compounds, when they are dissolved in water, can conduct electrical current even if they couldn't when they were solids. And those things are called ionic compounds. And the reason that they can conduct electrical current is because they are themselves charged particles. And the movement of charged particles is what electrical current is. So when those charged particles are freed from each other and no longer in the solid form, and they can move around in a solution, the solution then becomes electrically conducting, or an electrolyte. And then there are other substances that when you dissolve them still don't conduct electrical current. So these compounds must be held together by some other way than an ionic attraction of positive ions for negative ions. These things are called molecules. They're uncharged, and when they dissolve, they just remain uncharged particles, and so no current flows when these substances are dissolved in water. What we're going to do today is not how I prefer to teach. I'm going to just kind of tell you some things, and we're going to use some models that we have good reason to believe from in the scientific community are really what it would be like if we could see at the submicroscopic level and see at the atomic scale what structures of solids would be like. We're going to use these models to kind of work backwards and explain some of the properties that we see in different kinds of solids. It's not really easy to understand this stuff, and so I'm going to do the best that I can to try to explain why the properties that we see in different kinds of solids can be explained by their structures. And in reality, we knew about the properties before we knew about the structures. So this is not how the scientific community actually developed these ideas. We knew about the properties first, and that was part of the reason that we were able to deduce what the structure would be like. So we're taking a kind of a backwards view from how the knowledge developed in the scientific community. So I'm going to show you some models for a bunch of substances that are on this sheet that we have here on the screen, and look at how the particles are connected within the solids and why that causes those substances to behave the way that they behave at the macroscopic scale. So the first one we're looking at is argon. This is a modeling tool that we're going to use to visualize our different solids. I have the ability to rotate this around, and at the submicroscopic scale, this is how we think a bunch of argon atoms would be arranged. You can see that they aren't connected to each other by any kind of a bond. A bond in this modeling software would be represented by a sort of a stick. And so the atoms are there. There's something that must hold them together, because argon wouldn't be able to exist as a solid or a liquid without some attractive force that holds the particles together. But that attractive force must be very, very weak. How do we know that? Because argon melts at a temperature that's many, many degrees below zero, and it boils at a temperature also that's very many degrees below zero. So the forces that hold one of these blue argon atoms to another atom are very weak particles. Let's take a look at what this would look like if we had more atoms. So this is another view here. You can see that there's a definite structure to this. As I rotate this around, you can find a place where there are definite columns and there are definite rows. In 3 dimensions, this thing has a definite structure to it. So it's almost like if there was a grid work, there would be some intersections of these grid lines, and at the intersections are atoms. Let's go back to the note sheet. So in this note sheet, what we're going to do is we're going to fill in the columns here with the information that we're gathering from these models. For argon, the particles that are at the lattice locations, at the intersections of the grid, if you will, are atoms. And when a solid is this type of a solid, then we call that an atomic solid. The connections between particles, well, we have seen, because of the very low melting point and very low boiling point, that these are weak interactions. Let's call them weak attractions. The column that's all the way to the right in this chart is titled Notes About Properties. So here's where we're going to point out how the properties of the substance that we can see at the macroscopic scale can be explained by the submicroscopic structure of the particle. And because the attractions are weak, as we noticed when we were discussing this, there's a low boiling point. I'm going to say BP for boiling point, and also there's going to be a low MP melting point. In fact, argon exists as a gas at room temperature because of the fact that these interactions are very weak. Next, we're going to look at copper. Looking at the structure of copper that we have here inside this box, we can see that, again, it's atoms, but the difference is there's an actual bond between these atoms. Now, this bond is a kind of a bond that's different from an attraction because of positive and negative charge of ions. So these copper atoms are all atoms, but they have some electrons that are shared by all of the atoms. This is a property that's called covalent bonding, and this is a special case of covalent bonding where all the atoms share some electrons. So remember that electrical conductivity was very high in copper and in aluminum and in iron when we did our testing. It's because of those free electrons that don't belong to any particular atom, but all of the atoms are attracted to those electrons that have sort of left their zone, left that atom, and become part of the whole collective. So the sticks between these copper atoms, those represent bonds, an attraction of the atoms for those shared electrons that keeps the whole works together. If we look at more atoms, larger structure, this is what it looks like. And again, just like with the argon, if we line it up just right, we can see that there are definitely columns, rows. In 3 dimensions, there's a lattice work, a framework that we can see, and at each of the points where those, the lines of that lattice or framework intersect would be an atom. So let's go back to our notes and fill in information about copper. So for copper, at the corners, at the lattice sites, are atoms, and so this is, like argon, an atomic solid. Particles that are at the locations, as I just said, are atoms. What are the particle connections? The particle connections are not weak. They are actually pretty strong, or stronger at least, covalent bonds. Or we can call these a special case of covalent bonds called metallic bonds. And so that metallic bond is made, remember, by sharing pairs of electrons. And remember, that metallic bond is made by sharing electrons that belong to all the atoms, not to any individual atom. And all of the atoms are attracted to those electrons, having lost them and now being slightly positively charged. Now, the strengths of these bonds vary a lot in metals. So copper has a pretty high melting point, and so does iron and titanium and a lot of those kinds of metals, but there are some metals that have pretty low melting points. In fact, mercury is a liquid at room temperature, and gallium is pretty close to being a liquid at room temperatures. So we could say that there is varied melting points and boiling points for these things. So different metals are slightly different in their melting points and boiling points, but they're going to be better than nonmetals. They're going to usually have higher melting points than nonmetals because the attractions are stronger in most cases. Let's take a look at a nonmetal, graphite. Now, this is carbon. You'll see by looking at our chart here that there are 2 forms of carbon that we're going to examine. One is graphite and the other one is diamond. They're both pure carbon, but the arrangement of the atoms gives them different properties. So here's our model of graphite. As we rotate it around, we can see that we have some carbon atoms that are attached to each other, and then another group of carbon atoms that are attached to each other, but those two groups are not attached. There's no attachment between the two groups. Now, this is actually just a small segment of what graphite would look like. Let's get some more graphite in here. So more carbon atoms in this structure. And if you look at the structure, you can see that we have layers of carbons that are all attached to each other. So the carbons are held to each other by that same kind of a bond that the coppers were held to each other by. There's a shared pair of electrons. But unlike in metals, the electrons that hold one carbon to another carbon are isolated to just those two carbons. So this carbon and this carbon share that pair of electrons that makes up that stick, that bond. And you can see a kind of a six-membered ring, a six-atom ring. That structure repeats itself, and you can't see all of them in our model here, but they're all connected together. And if we kept expanding this, larger and larger, we would see that this is made up of six-membered rings in a sheet kind of atoms. So we have sheets of six-membered rings, and these would extend in many, many, many atoms wide and deep. But the sheets are not connected to each other by bonds. Instead, they're connected to each other by a weak sharing of some electrons that kind of live in between the sheets. And that's why graphite could be used as electrodes in our electrolysis of copper chloride lab, is because electrical current can flow in this nonmetal because of the electrons that are shared in these weak bonds between the sheets of atoms. This is also why graphite functions the way it does in pencil lead. Your pencil lead is actually graphite, and the sheets easily break apart from each other, but the sheets don't break apart within a sheet. So the sheets stay together, but they break away from other sheets quite readily. So when you're writing with graphite, you are breaking some sheets off, and they stick to the paper, and then other sheets stay on the lead and then break off at a different location as you draw your line or make your letter, whatever you're doing with your pencil. Graphite's melting point is actually very high, because in order for it to melt, in order for you to take the structure apart, you would have to be breaking up those individual bonds between carbon atoms, and those are really strong bonds. This is called a covalent bond. It's a kind of bonding structure that we haven't examined in detail, but it's made up of shared electrons, and they're very strong. While we're here, let's take a look at another form of carbon, diamond. Now, if you look at the structure of diamond, you can see that it's not in that flat sheet arrangement. This has a tetrahedral orientation. We can trace that out here. If you look at each carbon, it's attached. I'm going to rotate this just a little bit. There. Each carbon is attached to four other carbons. So there'll be one here, be another one here, and the angle between these is about 110 degrees. And then 110 degrees from both of these is another one, and then there's another carbon here. So this is a three-dimensional arrangement. It's not flat, of carbons attached to each other. So each carbon is attached to four other carbons, and then each one of those carbons is also attached to four other carbons. So this carbon is attached to this one, and then two more that we don't see because it's outside of our little one-cell box in our structure. So carbon is not a sheet. Carbon is a large continuous kind of, it's called a macromolecule when it's in the diamond form. Let's add more diamond. When we have more diamonds, or more carbon I should say, we can see that this makes it not a sheet structure like our graphite did. There's definitely some structure to it. We can find spots where we can see something that's similar to rows and columns. It's definitely a structure to it. but it's not that sheet arrangement. In fact, all of the carbons are attached to every single other carbon with no weak interactions anywhere. It's all those strong, like right here, that stick, that shared pair of electrons that keeps that carbons attached to other carbons. So diamond is very hard. You can't rub it across a piece of paper and have the sheets break apart from each other, because these carbons are all attached to each other very strongly. Its melting point is very, very high, even a little bit higher than graphite's, because you would have to pull all of these atoms apart from each other to make it melt. That's going to take a lot of energy. Let's go back to our note sheet and make some notes here. Graphite is an atomic solid. Diamond is also an atomic solid. And like all atomic solids, what's present at the lattice sites, at the intersections of that wireframe, if you think about it that way, is atoms. So they're atomic solids. What are the particle connections? These are very strong covalent bonds. So those covalent bonds, that's the shared electron pair bonds. And that's true for both diamond and graphite. But in addition to the strong covalent bonds, graphite has weak attractions between the layers. And that's what gives graphite the ability to kind of rub off on paper when you write with it, or serve as a lubricant, because it's easy to break those layers away. So, properties. Both of these things have very high melting points and boiling points. Both diamond and graphite have this characteristic. So these are atomic solids. We can see that there's a range. Atomic solids, or they're all three atomic solids, but their properties range from really low melting and boiling points to really high melting and boiling points, based on the kinds of attractions between the atoms. So atomic solids, it's hard to pin them down and say they're all like one characteristic, because they aren't. Let's look at carbon dioxide. Our next type of solid will be represented by this example. So here's our model of carbon dioxide. Now, again, this box shows like part of a molecule of carbon dioxide cut apart, and then part of another molecule cut apart because of the boundaries of the box. But in the middle here, you can see one complete carbon dioxide molecule. The black is carbon, the reds are oxygen. So it's CO2, one carbon, two oxygens. The bonds between the carbon and oxygens, those sticks, those are covalent bonds. So that represents a shared pair of electrons that both the atoms are attracted to, and that keeps them together in a molecule. Now that molecule is neutral. It's not like an ion. And so when you dissolve a molecule like carbon dioxide in water, it does not conduct electrical current because it's neutral. Let's make a bigger sample. Okay, so here would be a larger sample of solid carbon dioxide. And you can, just like always in these solids, you can see that there's some structure to the solid, and it's a little more complicated. It's not so easy to find rows and columns as it would be for an atomic solid, because what's at the lattice locations, what's at the intersections of that grid work, are not atoms but molecules. So it's multiple atoms. You can definitely see that there are carbon, two oxygen molecules, the CO2 molecules, in this structure, and that's what the whole entire structure is made up of. But there are no bonds between one molecule and another molecule. Those interactions are just weak interactions. They're held together by something, by some weak interactions, but it's like the ones that hold together argon, except just a little bit stronger. So it's pretty easy to make carbon dioxide melt and boil. So we don't see carbon dioxide as a solid unless we carefully prepare it that way, make it kind of cold, and we call that dry ice. So this is a solid that has molecules at its lattice location. That's called a molecular solid. The interactions within the molecules are strong. They're covalent bonds. So to make carbon dioxide into carbon and oxygen, that would require a lot of energy. But to pull one carbon dioxide molecule, like this one, let's say, away from this other carbon dioxide molecule, like this one here, that would require much less energy. And so lots of these things have very low melting points. Carbon dioxide is a good example. Going back to our notes, let's fill this in. The particles that are at the lattice site locations, in the grid work, at the corners of the grid, are now not atoms, but molecules. What are the particle connections like? Well, there's two kinds of connections. Internal, we have strong covalent bonds. Between molecules, we have weak attractions. So because the attractions between the molecules that make up the solid are weak, these things typically have low melting points, low boiling points. And carbon dioxide is definitely an example of that, because at room temperature it is a gas. It's not held together as a solid at all at that amount of energy. What's the kind of solid? This is called a molecular solid. The next on our list is sulfur. Let's take a look at that. This is a unit cell of sulfur, and this is also a molecular solid. It's not quite as easy to see. Sulfur comes in rings of 8 atoms. We can trace one out here. That's what a sulfur molecule is like. Now, when we were looking at a lot of them in this structure of the solid, it's hard to pick them out. We can maybe see another one here. 1, 2, 3, 4, 5, 6, 7, 8. There's another ring. But their view is distorted because of the fact that they're in all different orientations here. Those are molecules. What holds one sulfur atom to another sulfur atom is that strong covalent bond. So that stick there represents a shared pair of electrons, and this sulfur is bonded to that sulfur, and this sulfur is bonded to that sulfur with this strong bond. So it's not easy to break up a sulfur molecule and make individual sulfur atoms. That requires lots of energy. But you'll notice that between the sulfur molecules, there are no sticks. So one ring of 8 is attached to the neighboring rings of 8 by only those very weak attractions. So sulfur is going to have a pretty low melting point. Now, it's higher than carbon dioxide. Bigger molecules tend to have stronger attractions for each other, but it's still pretty weak, and so it's still going to have a pretty low melting point. So sulfur, like carbon dioxide, is a molecular solid. So that means at the lattice locations, at the points in the solid grid, are molecules. And just like what we saw for carbon dioxide, there are going to be strong internal covalent bonds in the molecules of S8, but between the molecules will be weak attraction. So that's going to result in low melting points and low boiling points. Next, let's look at sugar, C12H22O11. So sucrose is a pretty complicated molecule. It's got 12 carbons, 22 hydrogens, 11 oxygens, and inside of our little box here, our unit cell box, we can only fit one molecule. This is a molecule, and so we've got those strong covalent bonds again. So between carbons and oxygens, carbons and hydrogens, hydrogens and oxygens, we've got those strong shared pair covalent bonds. So to take a sugar and turn it into H and C and O atoms would require a very large amount of energy. Let's look at a larger sample of sugar. So here are several molecules together, and as we rotate it around, you can see the individual molecules. They're not connected with any sticks. So within the molecule, just like in the previous two examples, we have the strong covalent bonds, but between molecules we have only weak interactions. So sugar is not too hard to melt, but to take a sugar molecule and turn it into individual carbon, hydrogen, and oxygen atoms would require a great deal of energy. Sugar is also molecular. So at the locations in the crystal structure are molecules, and just like we saw with carbon dioxide and sulfur, we have two classes of bonds. Inside the molecule are strong bonds, between molecules are weak interactions. And so that results in the same properties in terms of melting point and boiling point. Low melting point, pretty low boiling point for sugar. This is sucrose, this particular kind of sugar. There's lots of sugars, but they're all molecular. One of the things that we notice here is that all of these molecular substances are made of non-metals. Carbon, oxygen, sulfur, hydrogen, those are all not metals. Let's look at a next category of substance, sodium chloride, NaCl. Let's take a look at that. Here's our model of sodium chloride. This is an ionic substance, so this is not molecules. This is just a stack of ions. These are the things that when we dissolve them in water can conduct electrical current. Here's the reason why. This purple thing represents a sodium atom. That sodium atom lost electrons, so it became positively charged. So is this one, also positively charged. This sodium, also positively charged. These greens represent chlorine. Those chlorine have gained the electrons that the sodium lost, and so they have become negatively charged. Oppositely charged things attract, and so that means there's an attraction between the sodium and its neighboring chlorines, and every chlorine is attracted to every other neighboring sodium. And that's what keeps this structure together. So there isn't a shared pair of electrons that keeps the structure together. It's in fact the individual particles, the ions themselves, are what's at the lattice locations in the structure, and they are literally attracted to one another, not to a pair of electrons that they share, because they happen to be oppositely charged. This is an example of an ionic solid. The kinds of attractions, the ionic attractions, are pretty strong. They're strong like covalent bonds. And so to melt this requires breaking them up, and so ionic solids have to have pretty high melting points. The other characteristic of these is once you do break them up, you now have moving charged particles, which is electrical current. If you provide a plus and a minus pole, like two electrodes that are positively and negatively charged, these ions are going to migrate. So you can do that in two ways. You can melt it, give it enough energy for the crystal structure to break up, or you could dissolve it in water, which also makes them free to move, like we did in the conductivity lab. Let's look at a larger sample. So when we look at this supercell here, a larger version of this, as we rotate this around, we can see this regular orderly arrangement of pluses and minuses, sodiums and chlorines, stacked together in such a way that it minimizes how much energy is stored in keeping them apart from each other. Opposite things attract, and so when you pull them apart from each other, that takes energy. The reason that they're stacked together so closely is because nature hates those high energy situations and is always trying to keep energy at its minimum by allowing them to come close to each other. Let's go back to our note sheet. So sodium chloride is an example of what we call an ionic solid. What's at the locations is no longer molecules or atoms, but ions. So these are charged particles. Things that used to be atoms, but have either gained or lost electrons to become charged. What holds the whole structure together? Strong ionic bonds. And ionic bonds are just attractions of one positively charged ion for a negatively charged ion. because those attractions are very strong, these things tend to have very high melting points and even higher boiling points. Let's look at another example, Li2O. Looking at lithium oxide, we can see another example of an ionic solid. Now this one is a little bit trickier to get your brain wrapped around because it's not one-to-one. The formula of this is 2 lithiums for every 1 oxygen. So the oxygens are red, the lithiums are purple here, and every oxygen has got 2 lithiums that go with it. Now in this single unit cell, it looks a little distorted, like one side's all purple and the other side's all red. That's just because of where they put the boundaries of this cell. The attraction is still the same. It's positive lithiums for negative oxygens, and that's what holds the structure together. Let's look at a larger sample. Again, you see this arrangement of positive and negatively charged ions that's held together in such a way that minimizes how much energy is stored in keeping them apart. In this model, we also see what looks distorted. It looks like it's all purple on one side and mostly red on the other side. And that's just because of where they put the boundary for the edge of the cell. They just cut it off between layers. You would see some reds kind of in the joints here if this model were to continue in all directions, sort of like it does here. Let's go back to our notes. Like sodium chloride, Li2O, lithium oxide, is a ionic compound, which means that at the lattice locations we have ions, charged particles, and what holds them together are the attractions of one ion for the other ion. So that's ionic bonding. And because those attractions are very strong between one ion and another, this is going to have high melting point and a high boiling point. Let's take a look at one more. This is silicon. You might recognize this structure. Here's this tetrahedral shape that we've seen before, where each silicon is bonded to 4 other silicons in this 110 degrees apart three-dimensional space-filling kind of structure. This is just like diamond, except it's different atoms. So when we have a larger sample of this, we're going to see the same thing that we saw with diamond. It's this very large structure that is, every silicon is attached to every other silicon in this large network. Those sticks, the bonds between one atom to the other, that's a shared pair of electrons, and that's a very strong bond. And unlike graphite, there's no layers here, so this means it's going to have a very, very high melting point, because in order to melt silicon, you have to break up all those extremely strong covalent bonds. Let's go back and make a change in our note sheet. Silicon is an atomic solid, but because all of the atoms are held together in a large network, covalently bonded, we have a special name for this kind of atomic solid. I'm going to call this a covalent network solid. So it's a special example of an atomic solid where all of the atoms are covalently bonded to each other. So that was also true for diamond. That was a covalent network solid. Rather than being held together by relatively weak bonds like argon and copper was, this is held together by extremely strong bonds. And so that makes this a very high boiling, high melting substance. So what's here at the lattice locations, it's atoms, because it is an atomic solid, but what holds it together is strong covalent bonds. And because those covalent bonds are so strong, that means it's going to have a very high melting point, very high boiling point. So now let's go down and look at some of these questions here. How can you distinguish between an ionic and a covalent compound? Well, if we look at our 2 ionic compounds, we notice that they're made of a metal and a nonmetal. On the periodic table, there's a dividing line, and the things that are to the left of the dividing line are metals. That's most of the periodic table. And things to the right are nonmetals. Sodium and lithium are both examples of things that are on the left-hand side of the table. They're metals. Chlorine and oxygen are both on the right-hand side. They're nonmetals. So if it's made of a nonmetal and a metal, it's ionically bonded compound. But here we see carbon dioxide and sugar. Those are examples of nonmetals. Sulfur itself is a nonmetal. So even though it's not a compound, it's covalently bonded. So ionic, metal versus nonmetal. When they bond ionically. Metals tend to give up electrons. Nonmetals tend to gain them. And so it's a natural fit for them to make an ionic compound by transferring their electrons. The metal will become positively charged, the nonmetal will become negatively charged, and then those two opposites attract. Nonmetals, neither one of them want to give up any electrons. They only want to gain electrons, and so they end up sharing those electrons to make those covalent bonds. How that exactly happens is for a different class, or at least a different unit, so we're not going to go into the details of that right now. But if it's made of all nonmetals, it's molecular, and it's typically going to have a low melting point, low boiling point. If it's ionic, that's because it's made of metals and nonmetals. Next question says, structurally, why won't molecular compounds conduct electrical current? So when they're solids, neither ionic nor covalent compounds will conduct electrical current because they just can't. The particles can't move. But in an ionic compound, the particles that make up the solid are charged particles. And so if you give them the ability to move by either melting them or dissolving them in water, those charged particles can now be the electrical current as they move. Molecular compounds aren't charged. Remember, they bond together with that different mechanism where they're neutral because they're sharing electrons in those strong internal bonds. So even if you dissolve them in water, even if you melt them and give them the ability to move around, those particles aren't charged. Next question, what is the primary difference between the bonds that hold together the atoms of a metallic solid and a covalent network solid? So the covalent network solids that we saw were carbon, graphite to some extent, and then also silicon. The covalent bonds are localized to two atoms. So in silicon and in diamond, that pair of electrons that make that covalent bond belongs to one particular pair of silicon or one particular pair of carbon atoms. They can't move around. They're localized. In metals, the pairs of electrons that hold together the structure, they're shared by all of the atoms, not any two particular copper atoms, let's say. And so those electrons have the ability to jump around and take different locations within the structure, which allows them to move. So diamond or silicon will not conduct electrical current, but copper or aluminum or some other metal that's held together with that delocalized covalent bonding can, because those electrons can move. It also has some consequences in how they behave physically. Metals, you can bend them and squish them around because as you move the structure around, the electrons can just reflow into new locations and bond the atoms together in a different physical shape. But that can't happen with diamond, for example. You can't bend a diamond. It will just crack. The same thing with a piece of silicon. You can't bend a wafer of silicon or a piece of sand, which is mostly silicon. You can't change those structures in that way because of the way the bonds are. They're not delocalized, they're localized, and so you'd have to break the structure completely apart in order to try and make it take a different shape. Explain the differences in melting points between the different types of solids based on structural features. I think we've already done that as we went through the chart, but if the attractions between the particles in the solid are weak, it will have a low melting point. We saw that with atomic solids like argon, where the weak attractions between atoms will break them up easily. The relatively weak covalent bonds, delocalized covalent bonds, in metals sometimes allow them to be broken up easily with low energy, and so the melting points are low. The weak interactions between molecules in molecular compounds allow them to be melted at low temperatures with little energy. The strong attractions between ions in an ionic compound and the covalent bonds in a covalent network solid make those substances have very high melting points and boiling points.